All right, welcome to the Explainer. Today, we're going to dive into a really fascinating new frontier, a place where two of the most powerful tools we have for understanding the universe are being smashed together: the rock-solid laws of physics and the incredible pattern-finding power of artificial intelligence.
So for centuries, right, we've had two totally different ways of trying to predict, well, everything, from where a hurricane will land to how a new material will behave. And both of these methods are incredibly powerful, for sure. But as we're about to see, they each have some pretty big blind spots.
So in one corner, you've got your classic physics models. These are built on what we call first principles, the fundamental universal laws that we know to be true. They're elegant, they make sense, we can explain exactly why they work. The problem? They're often just too simple. They're clean versions of a messy, complicated reality. And in the other corner, you have machine learning. It doesn't care about our pre-written rules. It learns its own patterns directly from just a ton of data. It's super flexible and can spot things we would totally miss. But it needs a mountain of data. It can be a black box where we don't really know why it works. And sometimes its predictions are just physically impossible.
So what if you could just build a bridge between these two worlds? What if you could take the strengths of both? Get a model that gets the fundamental, elegant laws of the universe, but can also learn from all the messy, complex details of real-world data. Well, this is where a really groundbreaking idea comes into play.
It's called physics-informed machine learning, and the core idea is pretty simple but powerful. You embed the governing laws of physics, things like conservation of energy or the equations for fluid dynamics, you bake them right into the AI's training process. You're trying to create a new kind of model that isn't just smart about data, but it's also wise about physics.
Okay, so this sounds great in theory, but how do you actually build this bridge? How does this work in practice? Well, it turns out there are three main strategies, or you can think of them as blueprints, that scientists and engineers are using to build these amazing hybrid models.
The first approach is probably the one that makes the most sense right off the bat. It's basically like giving your AI model a physics textbook. And then, when you're training it, you grade it on two things. Not just how well its predictions match the data you gave it, but also how well it follows the rules in that textbook.
And this has a name, of course. It's called a physics-informed neural network, or just PIN for short. And that's exactly what it is, a neural network that's being trained to do two jobs at once: fit the data and obey the laws of physics.
So here's the magic trick. You start with a standard neural network. You feed it some real-world measurements, just like you normally would. But here's the key. You also give it the physics equation that should be governing that system. And during its training, the model gets penalized if its predictions violate that equation. So it's constantly trying to find this sweet spot, a solution that doesn't just match the data, but also respects the laws of physics.
Okay, our next blueprint, this one goes a little deeper. Instead of just teaching the AI the rules after the fact, what if you could design the AI's architecture, its very brain, to have an innate, built-in understanding of those rules from the get-go?
The way we do this is by building in a really powerful idea from physics called invariance. And all this means is that certain things about a system don't change, even if you transform the whole system. You know, like if you rotate a spinning top, the laws governing its spin are still the same.
And this is where things get really beautiful. There's this deep truth in physics called Noether's theorem, and it basically says that for every fundamental symmetry you find in nature, there's a conservation law that goes with it. So, if your system has rotational symmetry, angular momentum has to be conserved. If it has time symmetry, energy has to be conserved. These aren't just good ideas, they're fundamental constraints on reality.
So how do you force an AI to respect these fundamental rules? Well, you've got a few options. You can actually design the model's architecture to be physically invariant from the start, or you could feed it features that are already invariant. You could even just show it a ton of examples that have been rotated or transformed. The bottom line is, by building these symmetries in, you guarantee its predictions are physically plausible by default.
All right, our final blueprint is, let's be honest, the most ambitious one of all. Instead of training an AI to solve one specific problem, what if you could teach it to learn the problem-solving process itself? What if it could learn the underlying operating system of a physical system?
And that's the whole idea behind something called operator learning. The goal isn't to find the answer to one problem. It's to learn the fundamental mapping, the operator, that takes any set of initial conditions you throw at it and generates the correct physical solution. And you can see just how different this is. A traditional model, even a PIN, is trained for one specific situation. If you change the conditions, you have to retrain the whole thing. But a neural operator, it learns the general rulebook. It can spit out solutions for brand new, unseen problems on the fly. It becomes a kind of universal physics solver.
And there are a couple of big players leading the way here. You've got depot nets, which learn by kind of simplifying the problem into an easier space. And then you have Fourier neural operators, or FNOs, which think in terms of waves and frequencies, and that makes them insanely efficient for really complex stuff like fluid dynamics. Okay, so we've talked a lot about the how, but what about the so what? What can these things actually do out in the real world? Well, let's take a look, because the impact is nothing short of revolutionary.
All right, look at this number. Under 60 seconds. What is that? That's the time it takes for Google's GraphCast AI, which is a physics-informed model, to generate a highly accurate 10-day global weather forecast on a single computer.
And to really get why that's so mind-blowing, you have to compare it to the old way. Traditional weather prediction systems take hours on massive supercomputers. So as you can see here, models like GraphCast aren't just thousands of times faster and way more energy efficient, they're also more accurate on over 90% of the key weather variables. I mean, this is a total game changer.
And look, this isn't just about better weather forecasts. This revolution is popping up everywhere. We're talking about optimizing 3D printing, discovering new materials, managing our power grids more efficiently, and building smarter robots.
So all of this, all these individual breakthroughs, they're all pointing to something even bigger. A new kind of holy grail for scientific research, really. The creation of a foundation model for science.
The big idea, and you can see it in this quote here, is to build these enormous models, pre-trained on basically all the scientific data we can get our hands on. Then scientists could take this massive pre-trained model and just quickly fine-tune it with a little bit of their own data to solve brand new problems. It would make scientific discovery faster and cheaper than ever before.
And that really leaves us with one final, pretty mind-bending question. We've been talking about teaching an AI the laws of physics that we know. But if an AI can truly learn the fundamental operating system of the universe directly from data, what new laws, what new physics that we don't even know about yet might it help us discover? It's an incredible thought to chew on. Thanks for sticking with us for this explainer.